Okay, good afternoon, everyone. We'll go ahead and get started here. My name is Diane Lechner. I'm the VP of Sales here with Midland Scientific. We're excited to partner with Hach today to have a presentation here on turbidity best practices. So we do have Luke Johnson here that I'll go ahead and introduce and hand over to him. As you see, you guys are all muted. Thank you for that. If you have questions throughout the presentation, go ahead and feel free to put those into the chat box. And then we actually will also include time at the end for additional questions for anything during the presentation. So Luke Johnson, like I said, who's joined us, he spent the first 10 years of his career working in various fields for Roche Pharmaceuticals, including a chemist, environmental engineer, and a quality control manager. Luke has been an applications chemist and a commercial channel manager with Hach since 2011. In these roles, Luke has developed many new applications, trainings, and marketing for Hach customers in multiple industries. Luke holds a BA in French with a second major in chemistry from Colorado State University in Fort Collins, Colorado, and an MS in chemical engineering from North Carolina State University in Raleigh, North Carolina. So go ahead and hand it over to Luke, and thank you all for joining.
Thank you, Diane. Appreciate it. And thank you, everybody, for joining. Like Diane said, if you have any questions, please feel free to put those in the chat. I'd be glad to answer those at the end. And if we don't get time to do that during the presentation, I'm glad to follow up with you afterwards as well. So don't hesitate if you have any questions at any point. So like Diane said, today we're going to be talking about turbidity, about some best practices and some applications. So let me jump to the next slide here and we'll look at the agenda. We'll start with an overview of turbidity and then move into the various measurement technologies for turbidity. We'll talk about some best practices and some surrogate applications. So before we get too into turbidity, I just wanted to talk about who Hach is. At Hach, it's our mission to ensure water quality for people around the world. So the way we do that is to make water analysis better. We're all about testing water. We're always trying to make it faster, simpler, greener, and more informative so that the customer, get it right the first time and every time. And really, turbidity is one of Hach's legacy analytical methods. We have a long history here, over 80 years in chemistries and instruments, and turbidity is one of those that has really played a strong part in our history. So we're very involved in approving EPA methods with the EPA for water testing, and we're a global company with manufacturing and engineering here in the US and across the world. All right, let's talk about turbidity. So first of all, it's good to know what is turbidity. Turbidity is the measurement of cloudiness or haziness in water. So if you've ever seen your drinking water, hopefully you can see right through it. That's clear, that's a low turbidity. If you've ever seen your dirty dishwater, maybe after you've filled up your sink and cleaned a bunch of dishes in it, there's a bunch of stuff floating around in there, you can't see through it very well, that would be highly turbid water. So specifically in turbidity, we're measuring how light reflects off of the particles that are suspended in water. And that could be anything. That could be, like I have listed here, proteins, minerals, bacteria, algae, silt, and clay. Like I said, the cloudier the water is, the higher the turbidity will be. But what turbidity is not is a measure of the actual particles in the water. So turbidity is really an aggregate measurement of everything that's making your water cloudy. It's not going to tell you how much silt is in your water or how much bacteria is in your water or how much one is there relative to the other. It's going to tell you everything all together. So in that aspect, turbidity is a measure of the relative water clarity and a great indicator of the quality of your water. Another thing that turbidity is very popular for is measuring the suspended solids. So like I said, it doesn't measure directly how much silt or algae is in your water, but it is an indicator of how much of that stuff is in your water causing turbidity. Some common turbidity applications. The big one, the history of turbidity, the main driver in turbidity development and measurement is drinking water. Drinking water analysis is very important. Obviously, you don't, like I mentioned, you don't want to be able to see anything in your drinking water. but even the things that you can't see can make you sick. And we in the United States have spent a lot of time treating our drinking water, getting better at it every year. And at some point we started chlorinating our drinking water to kill all of the bacteria and viruses in there. But some of the things are not susceptible to being deactivated by chlorine, specifically cryptosporidium and giardia can make it, the spores and the cysts of these microorganisms can make it through chlorination treatment. So the way that we remove those is through filtration, and the way that we test to see that we've removed those is through turbidity. So we're looking for very low levels of turbidity in drinking water to make sure that we've removed those cysts and spores. We're also looking in wastewater at higher levels of turbidity because we're not going to be drinking that, but we want to make sure that we're not discharging significant amounts of suspended solids into natural waters. In boiler water, common applications looking for corrosion and whatnot. So we're looking for extremely low turbidity. Beverage manufacturing, also extremely low turbidity because just like drinking water, we don't want things in there. Pharmaceutical manufacturing really could be anywhere along the range depending on what you're using it for. And then in cell culture, mid to high range turbidity. So a lot of different applications. This is not a comprehensive list, but there's a good possibility that you're using or could be using turbidity to measure something in your process in any number of industries. So how has turbidity been measured? This is really and how is it measured currently? This is really a history of Hach turbidity instrumentation right here. You can see we've been doing it for a long time. This is a candle turbidimeter through various iterations over the years, all the way up to our modern portfolio. So you can see that the measurement technology has come a long way over the years, and I'll go into more detail in the following slides. Like I mentioned, primary applications have been drinking water. And as far as major technological changes, the first technology for measuring turbidity was really the Jackson candle turbidimeter, followed by a photometer, and then a nephalometer, which is what we're using today. So this is how the Jackson candle turbidimeter works. Works by measuring the extinction of the flame. You can see you got a flame down here, and you add water to this tube and your eyeball up here, and you're going to be looking down the tube at the flame and adding water. And at the point when you can no longer see the flame, you'll mark the side of the tube there, and that corresponds to a particular turbidity value. So clear water, you can add more to the tube before the flame is extinct, before you can't see it distinctly anymore. Very turbid water, you can only add a very little amount. So this is a great initial measurement, obviously dependent upon a lot of different variables that are hard to pin down accurately, but this is really where the history of turbidity started. So in order to make this measurement more repeatable, more reliable, once photometers were developed, light transmission was used as the primary analytical measurement for turbidity. So in a photometer, we're going to shine light from a bulb through a sample. This is a turbidity sample here, and then some of the light will be scattered or absorbed by the sample, and then we're going to measure what's transmitted on the other side. So very easy to repeat, very regulated. You can get consistent results this way, and turbidity is still measured this way in some applications, but not for drinking water, not for those applications that require like really high rigor and good accuracy and precision. And the reason for that is because the changes in the transmittance of the light shining through here are really small for very low levels of turbidity. So it's really hard to measure with a transmission measurement. And for on the other end of the spectrum, for very high turbidity samples, multiple scattering across molecules really doesn't let very much light through at all. So then it's really hard to see that on the other side as well. So it's this measurement is really only good for a very a minimal range of turbidity values. So nowadays we measure turbidity with a nephalometer, and a nephalometer is very similar to a photometer. The big difference is that we move the detector 90 degrees. It's just a change on the axis of orientation. So rather than shining the light straight through, we'll shine the light into the sample, and then we're going to measure reflected light at 90 degrees of the incident beam. This is beneficial for a number of reasons that we'll talk about later on, but it's important to note that this is the standard now for in EPA and ISO reporting. You have to measure with a nephelometer. You can't measure turbidity with a candle or with a photometer. You must measure with a nephelometer. And that's what all of the modern turbidity analytical instrumentation is a nephelometer. And we'll dive into more of what that looks like in the upcoming slides. So this is an overview schematic of what a nephelometer is doing. We've got an incident light beam here. You can imagine this similar to the candle in the previous slides, shining through a lens, focusing it in on the sample cell here. And rather than measuring the light that's transmitted through the cell, we're going to measure all the light that is reflected off of the particles within the sample up at 90 degrees here. So this is the guts of a nephelometer. Very basic, very straightforward optical measurement. But there are a lot of different things that can affect the way a nephelometer reads turbidity. Specifically, the size of the particle will reflect light differently, the particle shape, the refractive index of the particle or of the solution that the particle is in, the color of the particles in the solution, and the concentration. All of those things can have different effects on the way that light is scattered, and the way that we measure it takes those various effects into account. So for instance, one of the factors affecting light scattering is the size of the particle. And what we have here is a diagram of the reflection pattern of various sizes of particles. The incident beam in all of these is coming in from the left-hand side, and then light is being scattered relative to that incident beam in various ways. So the first box we have here is the small particle. You can see there's a fair amount of reflected light coming off that particle in the forward scatter direction, but also back towards the incident beam. And for a slightly larger particle, you can see even more of the light is scattered in a forward direction and less light scattered back. And then for the larger particle, even more of it scattered forward, and then these kind of little bursts around the center here. One thing I wanted to call your attention to is that these little red arrows that we have in each of these, the amount of light scattered at 90 degrees to the incident beam is approximately the same for every size of particle. And that's one of the reasons why we want to measure at 90 degrees, is that we get a very consistent or much more consistent scattering of light at 90 degrees of the incident beam. So this gives us a better response in the modern nephelometer than relative to the photometer. Another effect that we need to overcome with our modern turbidity measurements is the effect of color. So either the particles or the sample itself, the particles or the sample matrix, if it has a color, that color will absorb light, and all the light that's absorbed will not be transmitted and will not be reflected. So if that light is absorbed, then less light will reach the detector, and the turbidity measurement will be incorrectly lower than it actually is, because that light in a clear matrix, or a colorless matrix, I should say, or with a colorless particle, more of that would be reflected. So how do we overcome that interference? The way we do that is with what's called a ratio detector. So a ratio detector measures at 90-degree incidence like a nephelometer, but it also measures the transmittance through the sample. And then it correlates those two together. So it can say, hey, this much light was going into the sample, this much light made it through in a straight direction, this much light made it through in a 90-degree direction, and then we can build an algorithm around that to tell us how much of that was due to scattering and how much of that was due to color, and then correct the scattering measurement, which is turbidity, for that color. Here's a schematic of what a ratio nephelometer looks like. It's very similar to the previous one I showed you. The light coming through the lens here into the sample cell. We still have the nephelometric 90-degree detector here, but we also have a transmitted light detector at 180 degrees, just straight through the sample cell. We also do some ratio nephelometers that are a little bit more sophisticated than this. This is the Hach ratio nephelometric system on the TL23 instrument. This is the light coming in through here and then interfacing with the cell. And we actually have 4 detectors on this ratio nephelometer. So we have the 90-degree measurement, we have the transmission measurement at 180 degrees, and then we have a forward scatter at about 135 degrees and a back scatter detector. And all of those are measuring the amount of light reflected at various angles off of each particle, and then correlating those to the light that is coming off the 90-degree detection, and correcting for color or size or amount of particles. And that's important because depending on the relative turbidity, more or less light will be scattered in the various directions. So this is a chart here that we've developed showing the light scattering, it reaching various detectors at various turbidimetric values. These lines correspond to the various detectors, and you can see that there's different amounts of light getting to each detector depending upon the amount of turbidity in the sample. At low levels, everything is similar except for the transmission one. Interesting to note here, which is why we don't use transmission anymore. But the various scattering, we're seeing a lot of that at the low levels with all of the detectors, with all of the scatter detectors. And then as the turbidity increases, the various detectors have different peaks and slopes depending on how high the turbidity is. So we have built at Hach into this ratio nephelometer the ability to correct for the various curves depending on which turbidity we're actually measuring a sample at. So ratio nephelometry really helpful for high concentrations and samples with colors. Like I mentioned before, this is the current Hach portfolio of turbidimeters. We have the TL23 benchtop nephelometer. That's this guy over here. That's a ratio turb, like I was describing. Here's the 2100Q portable nephelometer, which is just a 90-degree nephelometer. And then we have the two most modern, what we call 360 by 90 nephelometers, the TU5 benchtop and the TU5 process analyzer. Those are still using nephelometry, but they use a slightly different orientation of the optics to get a better resolution. So another thing that's critically important when you're measuring turbidity is having the right standard. Historically, turbidity standards, because you're not measuring just clay, or you're not measuring just algae in your water, you're measuring anything that could be reflecting light. Historically, standards have been made using what is maybe a representative sample. So a particular kind of clay, like kaolin, kaolinite maybe, or diatomaceous earth. And those things have a certain utility, but they're not very representative of all of the different kinds of particulates that could be causing light scattering. So along the way of developing turbidity instruments, one of the major developments was the synthesis of a turbidity standard. And the turbidity standard that we use today, and that is built into the EPA and the ISO regulations, is formazine. This is the synthesis of formazine here. But one of the benefits, or the benefits of formazine, is that it's a repeatable formulation, so anybody can make it. You don't have to go and mine the specific kind of clay or diatomaceous earth that we're using for a standard, but you can synthesize it yourself in your own lab. So it's very repeatable, and it also makes random lengths and configurations of this polymer. So that's really handy for simulating all the different shapes and sizes of particulates that are common in surface waters that we might be using for drinking water. It also makes like I mentioned, a wide array of shapes and sizes from less than 0.1 to 10 microns, and it's also stable, particularly at high concentrations. So at Hach, we manufacture these standards, Formazin, in a number of different configurations as a bulk solution that you can pour actually into a sample cell and measure, or as sealed vials. That's what's shown here. These come standard with our turbidimeters. These standards are stable and sealed and have a long expiration date, and they're good for calibrating your various turbidimeters. We also manufacture what we call Gelec standards, which are not Formazin and cannot be used to calibrate your instrument, but they're super handy for verifying a calibration. So these don't have Formazin; they're just a gel, but they also don't expire. So they're really great for a long-term just verification of your calibration, maybe in between calibrations with Formazin. And how do we put these instruments and these standards together to get the best measurement, our best analytical practices? So in theory, this is a pretty straightforward measurement. There's not like chemistry going on here. There's just a light shining into a sample and then measuring the light that's reflected off of there. But in practice, it's not especially simple to get a great measurement here. It requires a relative amount of technique and making sure that you're doing the measurement appropriately. So what we want to do is recognize the potential error sources and then make sure we practice the techniques to minimize those errors. So the main sources of error in a turbidity measurement are stray light. That's any excess light in the system coming from any source, anywhere, that contributes to a high turbidity measurement. So if you have extra light hitting the detector from somewhere, that's going to be measured as turbidity, and if it's not reflected off of the particulates, then that's a false high. So a couple places that could come from are the sample cells themselves, and we'll talk about that in the next slide, or gas bubbles that are in your samples. Those gas bubbles are not suspended solids. They're a temporary artifact of your sample, but those will also reflect light and be measured as turbidity. And then the other big source of error is an improper calibration. So we'll talk about both of these in a couple slides. This is a diagram of a turbidimeter showing all of the sources where you might get stray light. So this is the detector up here, the 90-degree nephelometric detector. And you can see that in a regular sample, what we want is light coming in to the sample and shining up here. But what we frequently get is light going directly to the detector from the lens. If it's out of focus, or if there's something on the lens, some dust or dirt or something like that, it can cause reflection directly from the lens to the detector. Or maybe light reflecting back from somewhere else within the instrument, the light trap here, or any of the other path length of the light shining back towards the detector. All of that will be read as turbidity, even though it's not turbidity. There's also light scatter from the sample cell itself. This is inevitable because the sample cell is visible. So we want to minimize that, and we want to take that into account in every measurement. So we want to take care not to get stray light off of the sample cell either. The big player in stray light, the big issue is just having a dirty instrument. So it's critical that you don't operate your turbidimeter in a dusty, dirty environment. And if you do, that you clean it or have it serviced, have it cleaned. The lens, the light trap, the lamp, just the internal guts of the instrument just has to be very clean in order to minimize stray light. And then, like I mentioned, we can also get stray light from the sample cell. So that can come from a contaminated cell. If there's schmutz on the inside of the cell here or scratches or something on the outside of the cell, light can hit that and reflect to the detector, and that is not the turbidity of the sample, obviously. That's just light reflected off of the sample cell, but you'll be getting a false high reading. So we want to make sure that sample cells are very clean and also that they're well maintained. If you have cells that are scratched or have been dropped a number of times or maybe even just once, it's best to just replace that cell. They're not terribly expensive, and you'll get better readings. So your goal is to make the cell as invisible as possible. The light needs to go right through there and not be interacting with the cell in any way. So like I mentioned, you want to make sure that they're very clean on the inside and the outside. You can do that with detergent, with acid. You can run it through an ultrasonic bath to break things off of the inside or the outside of the cell. And then finally, you always want to rinse with filtered deionized water. You don't want to have anything that you're storing in your sample cells that might stick to the glass or cause some sort of imperfection. Also, if scratch cells are kind of inevitable to some extent, so the best way to minimize the effects of scratches is to apply a silicone oil to the outside of the glass, and that's pretty straightforward. We provide silicone oil with all of our turbs, and you just put a drop on like a Kim wipe or even on the vial itself and just wipe it around. You don't want to leave like big blobs of oil on there because again, that will be read as turbidity, but really you're just trying to fill in any scratches with that oil so that you don't get a reflection from those scratches. And then finally, one way to make sure you have consistent results is to always index your sample cells. So our turbidity cells have this black triangle here, that's the index mark. And you always want to put that in the same orientation in the instrument. That way, any kind of issues that you might have with the cell, and hopefully you don't have any issues, but if you do have any issues, like any scratches that you just can't work out, they will always be accounted for in the same way, right? They'll always be interacting with the beam in the same way. If you didn't index and one time you measured and you just didn't have any reflection off of that particular scratch, or at a later time you turned the vial and you did have reflection off of that scratch, you would be building in that scratch, the turbidity off of that scratch into your measurement. So you want to make sure that you are putting the cell in the same configuration every time you put it into the instrument. And there's actually a technique around making sure that your index is appropriate, that you're getting the best results, but I'm not going to get into that in this presentation. I highly recommend checking out the manual for your instrument as far as how indexing is performed. And then the other big source of error is an improper calibration. So turbidity is kind of hard to calibrate, particularly at the low end of the measurement range. The EPA says calibrate according to the manufacturer, and as the manufacturer, Hach recommends that you calibrate with one standard. If you're measuring at the low end of the range, with one standard, not less than 20 NTUs, and NTUs are the nephelometric turbidimetric units. Those are the units of turbidity. Even if you're measuring down in the 1 NTU range or less than 1 for drinking water, perhaps, we still recommend that you calibrate with a 20 or 40 NTU standard. And the reason we can do that is because turbidity is highly linear, especially less than 40 NTUs. There's like a theoretical zero of turbidity, and that corresponds with a zero response at the detector. And from that point all the way out to 40 NTUs is extremely linear. So if you can calibrate at 40 accurately, then your calibration curve can go right through zero and your measurements will be good all throughout that range. The reason we want to do that is because a small error at 40 won't really affect your measurement down here at less than 10. But if you were to calibrate at less than 10 and you made a measurement error in your calibration for some reason, your calibration curve will be significantly off throughout the entire range. So it's just a best practice to calibrate, because we have the benefit of a linear measurement. Best practice to calibrate all the way out at least 20 NTUs. Now that doesn't really that doesn't hold for past 20 NTUs, and that as you might remember, is because the curve is not linear. I think I showed you a few slides earlier at the various detectors. The curve is not linear outside of 40 NTU. So you really need to calibrate throughout the range, like you would with maybe a colorimetric measurement for higher range samples. But for low range samples, it's preferable to calibrate with one standard. So let's talk about some of the surrogate applications. And really with turbidity, everything's kind of a surrogate application, because turbidity is, it's not measuring a thing, right? It's not measuring clay, it's measuring everything that's in your water. So turbidity itself as a concept is kind of a surrogate application. The big application that everybody uses outside of drinking water, that everybody is using turbidity for, and you may be using yourself, is for total suspended solids. So obviously suspended solids are the stuff that's floating around in your water and that's making your water cloudy. And turbidity is one way of measuring that. And the total suspended solids method, the gravimetric method, is another way of measuring it. Actually, I should say the gravimetric method is the way of measuring total suspended solids, and turbidity is a useful correlation with TSS. So if you've run TSS, you know that it's it can be kind of a time-consuming method. You have to take a grab sample of a certain volume of water, take it to the lab, pour it through a filter, weigh the filter, pour the sample through the filter, dry the filter, and then weigh back the filter with whatever the residue, whatever the suspended solids from the sample are, and then run a calculation to see, what's that weight difference versus the sample volume. So that's the official way of measuring total suspended solids. You can correlate that with a turbidimeter, and rather than running that lengthy lab procedure every time you want to know your suspended solids, you can instead just run a turbidity. Excuse me, it's hard word for me to say, a turbidity analysis, and that just takes a few seconds of, push a button, shine the light through the sample, and boom, it'll tell you your turbidity, and then you can correlate that to your suspended solids with the coefficient for whatever your matrix is. Generally, wastewater matrices have a pretty standard correlation coefficient. This could be different for different matrices, because like I said, sample size, sample color, types of particulates, those all have a different response in turbidity. So if you have a highly variable stream where you're not getting the same types of particulates all the time, it's probably worthwhile to perform multiple calibrations or correlations with your turb and with the TSS measurement. But if you have a very consistent stream, like you're always measuring at the effluent of your wastewater plant, and it's going through the same process all the time, then your coefficient should be the same pretty much all the time. Another application for turbidity, a surrogate measurement, is boiler corrosion monitoring. And boiler corrosion is a really pernicious issue in the whole steam cycle for power generation, not just boilers. And it's usually present as particulates. So the iron will dissolve, and it will be present in the steam or the condensate or the boiler water as either one of two primary oxides, iron oxides, either magnetite or hematite. Those are two different colors. So this application is kind of cool. You get to see the way the turbidimeter responds differently to these two different two different oxides. This is a calibration curve showing the turbidimetric response to both hematite and magnetite, and you can see turbidity on this axis versus the concentration of iron here. The red hematite, you get a higher response in turbidity for the same values of iron than you do with the black magnetite, and that is because the black particulate is absorbing more light than the red particulate. So interesting application for turbidity that is highly color dependent. Another surrogate test here is silt density index. Silt density index is itself kind of a surrogate test for the for membrane fouling, for reverse osmosis membranes. There are a number of different fouling mechanisms that can cause an issue with your RO membrane. And one of those is particulate fouling. So SDI as a test measures all of those combined, sort of, and turbidity can be useful for monitoring one of those fouling mechanisms without a lengthy manual grab sample kind of test, which is what SDI is. And finally, another common application that we see is for measuring optical density in cell growth applications, kind of in like biopharma industry in particular. So if you're growing cells in a matrix, those cells are going to reflect light because they're suspended solids, just like clay or whatnot in a water matrix. So you can monitor your cell growth with turbidity just to see when you're at a certain point on your curve here. And OD 600 is the test that people are frequently using for that, which is actually a spectrophotometric method, but yeah, it's actually a better measurement to use it with a nephelometer, a more reliable measurement. So that concludes my presentation on the history of turbidity and some best practices. And thank you guys for your time. Are there any questions in the chat, or Paula, or Diane, did we get any questions?
I have a question here, real quick. So what do I do if I have bubbles in my samples?
Okay, yeah, good question. Bubbles are not, I mean, that will be measured, like I mentioned earlier, it will be measured as turbidity, but they're not typically what you want to be measuring as turbidity. So there are a couple ways to remove bubbles. The obvious one is just to let your sample sit for a while and let the bubbles kind of sparge out, or you could apply vacuum to pull bubbles out of there. I will say it's important when you're prepping your sample not to shake the sample vigorously, or standard for that matter, because every time you do that, you will introduce bubbles into your measurement and then you will get a false reading. So best practice is to take a sample and in a gentle fashion, invert it a number of times to suspend any of the particulates that are in the sample and not entrain bubbles. But if you do have bubbles, you can pull them out with vacuum, or you can just wait for the bubbles to disperse.
And then I got a question here from the chat. It says, I've heard about laser instead of light being used. Can you discuss this?
Yeah. So actually, some of the turbs that I showed earlier do use lasers. It's really a matter of what you prefer, I guess. Historically, like I mentioned, we had candle flames, and then we moved to an optical like tungsten bulb, which is giving off the whole range of white light, and we'll filter that down to a particular wavelength depending on what the application is. In the US, we use the EPA wavelength, which is somewhere between 400 and 600, according to EPA regulations. In Europe, mainly, according to ISO, we'll use a higher wavelength, around 860 nanometers. But a laser A laser turb is just using a different light source. So rather than using the entire spectrum like a tungsten bulb and then filtering it down to the wavelength that we want, we'll just use a laser as the source that is already only emitting light at that wavelength. There are benefits obviously to that. Lasers last a long time. There's less work in the optics as far as filtering. They're very consistent light source, less fluctuation, and yeah, Hach offers those in a variety of instruments. Some of the ones that I showed earlier, the TU5s in particular, but also the well, I'll just leave it at that. The TU5s in particular are using lasers rather than tungsten bulbs.
Thank you. And then one other question here, how many TSS samples are needed for a calibration?
Usually just one. I mean, it like I mentioned before, it depends on what your stream is. If it's a consistent source, then you can usually get by with just one. You might want to check it periodically, like anytime you anticipate or you have had a process upset or something like that. But most of the time, for most of the customers that we have, one will get them by, and a lot of people don't even use calibration. They might just use a generic factor that somebody has calculated rather than calculating their own. But I would say if you are at extremely high turbidities and a variable like source water, it would be worth taking multiple samples to perform that correlation, that calibration over various turbidity levels. But generally speaking, just one.
Okay. And then a follow-up from the chat, it says, are there wearable parts or consumables that need to be replaced for this?
Not a lot going on in a turbidimeter. The bulb itself is really the only thing that you need to be concerned about going forward, and that is just a matter of is it have its original intensity or sufficient intensity, or kind of consistent light production. So it's a good idea to calibrate. Yeah, I mean, you should calibrate like once every quarter is what Hach recommends. And during your calibration, you should notice whether or not you have an issue with your light source. But it's not a bad idea to have a maintenance, like a service performed annually, just to clean out the instrument, so you make sure you're not getting stray light, and also to verify that the lamp is still in good condition.
Perfect. Any other questions for anyone on the phone? All right. Well, if not, we'll go ahead and end the presentation here for today. Thanks again to Luke and the folks at Hach for joining us. For everyone who's on the call here, we will have share the presentation with you afterwards. You guys have that. And if there are any questions, please feel free to reach out to us, and happy to help. And have a great rest of your day. Thank you all.
Thank you.